Morning, everyone. So yesterday we started looking at nuclear reactions. We introduced two key terms. One was fission, which is taking relatively heavy nuclei. We're going to do examples of uranium in this lesson here. The heavy nuclei here, for some reason their nucleus is unstable, undergoing radiation, whether it's radiating particles or radiating away energy, it ends up increasing this key concept here on binding energy per nuclei. We're going to look at fusion in a separate lesson tomorrow. Essentially the same thing. When we take lighter elements instead, fusion actually implies gluing atoms together, forming nuclei, and in that case there, we still end up forming elements closer to the iron 56. That's the most stable, energetic isotope that actually has the highest binding energy per nuclei. It is the most stable element that we have. We talked about here the key terms were mass defect as well as binding energy. Essentially, if I added up all the nuclear masses, the rest mass of a proton, neutron, you could add electrons if you wanted to, but mainly it is just the neutrons itself. But if I add up the Lego pieces, the protons and neutrons, and I compare it after the atom itself forms, I may be made out of exactly the same protons and neutrons, but because there is some binding energy from the strong nuclear force, we end up realizing that some of the mass has actually been lost. We call that a mass defect, and then we saw two examples from yesterday's lesson. How do we convert mass over to energy using Einstein's equation mc squared? So make sure you do practice some of those numerical calculations here. Today I want to flesh out with you a little bit more with fission reactions, actually getting more into the broad stroke of how have we been able to use these for nuclear power plants, more on some sort of safety considerations along with doing fission, and then tomorrow we'll come back and we'll take a look at fusion in the same way. So let's go back to our binding energy per nucleon graph. Again, on the y-axis here, it's plotting this average binding energy. Once the mass has been converted over to energy, this is the amount of energy that gets released. They've divided it by the number of nucleons. Then I can make a fair comparison. We have relatively light things on the left. As I get to the right, I end up getting heavier and heavier. For the lighter things, we notice that protons and neutrons are sort of in lockstep. When I pick up one proton, one neutron, right, that's enough, right? There's not as much repulsion, but it doesn't take much. As you get too many protons, we need way more neutrons to actually have enough strong nuclear force to overcome the repulsion. In this case here, we're going to focus on mainly things that are heavier. So we're going to look at the last stable isotope. Uranium has two common isotopes here, the 238 and the 235 form. We're going to see that its binding energy here is roughly about 7.8, 7.9 or so. And then what's going to happen here is if I allow these heavy nuclei to actually undergo fission, fission means break apart, the daughters, which are tinier, you'll notice that they actually steadily get higher and higher on this graph here. And remember, the higher we are on the graph, the more stable we are, because that ends up releasing more energy per nucleon. It can actually release energy until they're iron. We're never going to do like a mechanism going all the way to iron, but in fact, any sort of progression I get closer and closer to iron is enough. Even this increase in binding energy to, we're going to see things to radium, to radon, things like that, it's already increased energy, and that's the energy that we're hopefully going to harness using a nuclear power plant. Tomorrow we're going to come back and look at fusion in the exact same way. In that case, their fusion means you're going to take lighter elements at really hot temperatures and high pressures. We're going to glue them together. And again, they're going to increase binding energy. You'll notice they actually increase binding energy quite a bit faster than your fission reactions. So that's going to be a difference we're going to see in tomorrow's lesson. So whether it is fission, breaking up, or whether it's fusion, forming, gluing together, the closer I get to iron, the higher up on this graph I am, the more stability I'm getting, I'm going to end up releasing energy that can be harnessed for nuclear power. So, more detail for fission here. Mainly, we're going to look at one fission reaction here, which is the fissile, or the reactive form, the radioactive form of uranium is the 235 isotope. Unfortunately for us, uranium comes to us as a mixture. Most of it is actually the heavier uranium-238. So let's take a look at what uranium-235 can do. Here's how nuclear power plants currently are designed. So I'm going to start off with the uranium-235. This is the active form. Again, unfortunately, this is not the most stable isotope. What we're going to do is we're going to fire a source of slow-moving neutrons. Basically, I want these neutrons here to be slow-moving enough that the uranium-235 has a chance to actually absorb that neutron. That neutron gives it a little bit of excitation because it's like, oh, now I have an extra neutron. Now I'm going to actually break up. So in this case here, that neutron gets absorbed in, and basically it ends up fragmenting this uranium-235 into many bits. For simplicity, we're just going to do 2 bits, but it could, although we're going to want a really good control of how many neutrons actually attack this uranium-235, there's no real easy way to actually control what particular daughter isotopes are released. The reason why we want to monitor how many neutrons are actually being released, however, once uranium here on this diagram here is broken off into 2 fragments, they don't have to be even fragments. Usually one is lighter, one is a little bit heavier. We refer to both of those as daughter isotopes. But you notice as we go through this fission reaction, it ends up also releasing off neutrons. Now those neutrons here can then go and trigger other uranium-235s to cause them to undergo fission as well. You see that 1 neutron has broken off to become 2. These ones here now trigger 2 other nuclei here. Those 2 successively will trigger 2 more neutrons here. If I don't have, we need to actually control rods and moderators to actually control not only the speeds of the neutrons, but to hopefully soak up some of these extra neutrons. It's very quickly that this might be to spiral out of control. We refer to that as a chain reaction. If we have a very devastating accident here, we call that a nuclear meltdown. So definitely nuclear energy here, even though atom by atom, it's not a lot of mass that's being conserved, but we're going to see that in comparison to the fossil fuel source we've been using, if we can harness this energy slow enough in a safe enough way, this can actually provide a lot of the electrical and energy needs that we have. Lots of safety precautions, though. In this case here, we see from the reaction, I definitely want to have some good control with how many neutrons are being released and how quick these neutrons are actually being added. So imagine you were designing a nuclear power plant. You have some uranium-235 nuclear source here. Where you're going to want to start off is you want to start off with enough uranium-235. If you only have sort of a couple atoms here, it may not have what's referred to as the critical mass. The critical mass is sort of how much uranium-235, as an example in this case, how much uranium-235 I would need so that when I start firing my slow-moving neutron, even if I am controlling how many neutrons are getting released, usually we try to control it so that only 1 neutron is actually being released per fission reaction. So I sort of have the same number in and same number out. That way I don't let it spiral out of control. But I want to make sure that this leaving neutron has a good chance as it travels through my sample to interact with another uranium-235 to trigger yet another reaction. So I don't want it to chain reaction out of control leading to meltdown, but I do want to design my apparatus in such a way, have enough uranium-235 that there is a good chance 1 comes in, it breaks up uranium-235, I already get some energy. I end up controlling only 1 ends up leaving, but this neutron here has to have a good chance to actually run into another 235. I do want it to be able to trigger the next reaction, but I do want to control it so it doesn't get out of control. So we call that term here the critical mass. How much fuel do I need so that the fission reaction can be self-sustaining, so that I don't need to constantly be supplying neutrons at risk of meltdown? So in this case here, if I have too little, right, so I fired 1 neutron in, maybe 1 neutron came off, 3 neutrons in, maybe these ones here don't have a good enough chance of running into uranium-235s, maybe enough of them leave and they don't trigger enough reactions. Or I have too much and sort of more than the critical mass here. 1 is triggering 3, and each one of those are triggering 3 here. This one here might spiral out of control. So for your nuclear power plant, you want to make sure for that sample you have the critical mass. Just enough fissile material, just enough fissionable material to self-sustaining so that it can continue, so that you're not constantly having to trigger the first reaction. So we're going to take a look at this fission chain reaction that we diagrammed here. They call that fissile material. That's the radioactive material. That's the reactive form. The waste contains mostly unreacted 235 as well as some plutonium daughter isotopes as well. We're going to find one sort of ongoing safety consideration here is, even though we've been able to harness the energy from our radioactive uranium-235 form, what do we do with all this waste? A lot of these themselves are radioactive. When we start taking a look at half-life again in tomorrow's lesson here, the half-lives tend to be very high as well. So what do we do with all this waste, or what can we do with it? Fortunately for us, we're going to see how we actually separate for the more useful form uranium-235, but that's one sort of nuclear power plant design. Another power plant design here actually was able to utilize some of this. This PU here is actually plutonium. Plutonium here was actually sort of engineered in a different sort of power plant model here, and we actually managed to take this plutonium, which was a waste out of our first power plant here, and we actually managed to use this plutonium-239. We run them through breeder reactions or breeder reactors. and basically use this to harness even more energy. This one here does have advantages over the uranium-235. As we step across some of these slides here, we're going to see some of the details. So the reason why these are called breeder reactions is because first thing, the source is actually very plentiful because it's just a waste product out of my first power plant. But the other thing we're going to have to do here is this one will not require the same enriching that we're going to see for uranium that we need. So far we have two possible designs for nuclear power plant. The nuclear power plants that we have in our world today are both fission reactions. We haven't been able to harness fusion reactions. We'll see why in tomorrow's lesson. But so far one has a design of using uranium. The waste out of that uranium design here is one possible daughter isotope is plutonium, and we managed to reuse that waste or plutonium with our second design here called the breeder reactor. So let's go back to our first design here for using uranium-235 and uranium-238 here. How can we manage to enrich the sample enough that we have the more useful 235 form? What are some of the limitations with that? And then in contrast, we're going to see with plutonium's design as well. So back to the uranium field here. We're going to start off not just taking chunks and chunks of uranium. That will probably be solids. It's very hard to react solids. So what we're going to do is we're actually going to use uranium in the form of a compound. And the compound that we're going to use is actually UF6. So in this case here, at first we would say uranium is a metal, fluorine is a non-metal. This should be ionic. We're going to see as we look at this compound in a little more complexity here, we're actually going to see that there are unique features for this UF6 that allow it to be a good source for a nuclear power plant. And what we're going to do is we're going to compare this UF6. It's the uranium that I'm caring about. This uranium could be in the 235 form, the fissile form, or the 238 form. But in both cases, we're using it as UF6. We're going to see it's actually a gas at room temperature. And what we can do is we can separate for the useful 235 form using either diffusion or effusion, we're going to see in a little bit here, or centrifugation, basically spinning it through, and basically what we can do is we can select for the 235 form versus the more abundant 238 form. That process there is called enrichment. Just for comparison, as we look at why UF6, they're going to compare it to a compound called UO2. Now this one here is actually an ionic compound. As an ionic compound, you would just imagine here, it's an ionic lattice. Ionic bonds are really strong. These charges are fairly high. It's a nice crystalline solid here, really high melting point. You can imagine needing to melt it. This is just into the liquid state, not even gas yet, some 2,800 degrees or so. So just as a comparison, we're going to be using UF6, but this is the more typical compound that we would expect for uranium, UO2. How about UF6 that we're going to end up using? Again, specifically here, UF6 is actually going to take up some covalent nature. We're going to see it actually has a nice octahedral geometry here. It's an octahedral geometry. It's actually non-polar overall because although it does have polar bonds, although fluorine is the most electronegative, that's going to come back in a little bit here, you'll notice that I'm getting pulled evenly, very symmetrically here. Overall, I'm actually non-polar. We know from our chapter 4, if it's nonpolar, we only have really, really weak London forces to deal with. Now, generally, when we are dealing with London forces, the more charges we have in general, like just the background attractions would be strong enough to make me sort of have higher melting point, higher boiling point. In this case here, we're going to see it's that very same. Fluorine is a very electronegative element. It wanted to be a full -1 here, but what's going to happen here is these negatives here surround this uranium so well that when this UF6 is close by another UF6 here, these partial charges actually repel each other well enough away that even though I have a lot of charges, right, uranium has a ton of charges, the London forces should be pretty intense, but because of this really intense repulsion all around this uranium, we end up having relatively weak London forces. So in fact, we don't need the 2,800 degrees we saw in the other slide with UO2. It even sublimes. It goes straight solid to gas at slightly hotter than room temperature. Because it is a gas, it's a lot easier to run through my device. So again, we're going to take a look. UF6 is the form that I actually put it into my power plant. We still have a problem because uranium has two common isotopes here. Uranium could be the 235 form. That's the useful form. Unfortunately, some 98-99% of uranium is actually the 238 form. We need to somehow enrich, select for just the lighter form because the 235 form is good and the 238 form is unreactive. So make sure you know this key term here, uranium enrichment. I want to be able to select for the fissile, the radioactive form of the 235. It's not the 238. Unfortunately, if you just take a naturally occurring sample of uranium, it's our last stable isotope, less than 1% is the useful form. Most of the 99 or whatever extra that is, that one is the less useful form. So what we're going to have to do is we need to enrich it so I can select for, out of all the uranium that right now is 238, how can I select and choose for just the 235 form? There's going to be two sort of general ways that we're going to just take a scan over here. The two ways here, first is they are isotopes to each other. So isotopes means they are the same element, same proton number. Their chemical reactivities are the same, so we can't use a chemical way to separate. But one way we're going to do is they actually diffuse. When we talk about gases traveling through a tiny pores, we can call it effusion as well. But we're going to see that because of mass, the diffusion rate, the average speed that these particles travel off at, is actually going to be different. I'll show you a derivation when we get to our textbook slides here. We're going to find that the rate between these two particles is actually inversely related to the square root of their masses. So if I have one that's like uranium 238, one that's uranium 235, because of the slight difference in mass, they're going to be traveling slightly different speeds. In fact, when I actually do this in a little more detail here, I end up taking the 238, the 235 form. How come this one here isn't just 238, 235? Is because they've also added in 6 times fluorine's mass, so fluorine is 19. That's why it's slightly heavier. But I can see the heavier number here was the 238 form. If I do this square root with this mass ratio here, I end up getting these, the speed of the gases are actually going to be different by 1.004. Not by much, you see, right? The mass isn't that dramatic. There's also the square root as well, but there is a difference. So what can happen here is I can run it through some sort of permeable membrane, and what's going to happen is, because I had the heavier one here, that's the M2 here, that means the 238 will be slightly slower than the 235. The 235 will go 1.004 faster than the 238. It's going to diffuse a little bit quicker. So what we can do is we can leverage this here. Here's a nice little diagram of this uranium enrichment here. You can imagine starting off just pumping in just straight UF6. Majority of those are uranium-238. There's the odd fraction of 235 here. We're just going to let them, as a gas here, spontaneously here just collide and perhaps hit this permeable membrane on the top here. Because there's a slight imbalance that uranium-235, that lighter isotope travels a little bit faster, given the same average temperature. Those faster particles will travel through the permeable membrane quicker than the 238. It doesn't have to do with size. It's not like, oh, I made it small enough. These are already molecular in size. It's going to be hard to make it that small porous. But we're relying on this Graham's law, this effusion law. Basically, that 1.004 feature, that difference allows the uranium-235, because it's a lighter atom, to actually separate from the 238. It's not by much, however. So after the first one here, I wouldn't expect to get a full, a lot of the 235 and not as much 238. But what's going to happen here is maybe I'm going to cycle this gas many, many times through the same chamber, or maybe through a cascading chambers like that. And what's going to happen is every time I give it a chance where those fast-moving particles can actually travel a little bit quicker, now we have a gas that's enriched with 235. In fact, maybe I might run this that already has a lot of 235 here, maybe run it through even more permeable membranes here. I keep selecting for this 235, the enriched, the slightly more useful form. As you might imagine here, this takes a long time, so that's sort of one limitation of this sort of nuclear design. Second way we can do it here, again, leveraging a physical property, is because they are different in terms of masses here, we can run it through a centrifuge. Now, there's many different designs of centrifuges, but essentially they all work the same way. By doing this sort of spinning at really high speeds, what's going to end up happening is the heavier particles end up going to the outsides, whereas the lighter particles end up having a smaller radius. So what's happening here is, because of the spiraling here, because the 238 is a slightly heavier gas, they tend to be spun to the outside. I somehow designed in such a way that those outer gases get depleted and those outer gases leave. The uranium-235 that actually travel in smaller radii, they stay closer to the center, and basically I can collect this 235 form separate from the 238. So far we've seen two ways that leverage the physical characteristics. Why do we need physical? Is because both uranium isotopes are the same chemical, their outward structure is the same. I can't run a chemical reaction to actually separate them. Not true for plutonium. We're going to see that on the textbook slides here. But so far you do want to know this word here, enriching, is selecting for the fissile or fissionable 235 form. They both rely on physical characteristics. Either we run it through a effusion law here, run it through just diffusion many times, or run it through a centrifuge. Also, this needs to be cascaded many times, and basically I slowly select for the 235 form. Now, I mentioned here there's a lot of potential safety risk here. Here's just a couple of slides just to introduce them to you here. The risk can be a couple different ways. They can be health considerations, so the workers that are in these nuclear power plants, people that live in cities with power plants. What do we do with the waste afterwards? So even though maybe I enriched uranium-235, I have a lot of the good reactive form, but what do I do with all the waste that's also radioactive? Some of them have half-lives on the order of millions of years, so how do I dispose of it? There's a risk of meltdown, so we talked about critical mass. I do want to have enough of it to be self-sustaining, but if I'm not having control rods and moderators to actually control the neutrons quick enough, it can really easily spiral out of control. So there's sad stories of that happening, as well as risks that, this nuclear technology here can be used for weaponry here, although because this needs to be enriched many times, the weapon argument here is not as on people's radar as the other plutonium design that we're going to see. So let's just look at health effects in a little more detail here. All sorts of these radiations, we're going to see the alpha, beta, gamma a little bit more in tomorrow's lesson, but basically all these types of radiation, they can actually interact with matter, like the matter in your body here, and what's going to end up happening here is, because our bodies are made up of mostly water here, this radiation, be it alpha, beta, or gamma, can actually start causing nuclear reactions on this water. So what ends up happening here is this radiation here so far has ionized the water. So it's removed this electron here. Now I have a sort of a radical form of water. Now this one here is now very deadly because it can, as a radical, as an unpaired electron, it's now ready to react with a whole bunch of other things. So we see some examples of this on the other side. There's the ionization. Other potential things that it might interact with in your body here. I could also add an electron to water. I can form a hydroxy radical. Again, it's that unpaired electron. That's the hydroxy radical here. These unpaired electrons here will react with whatever it collides with, try to pair up these electrons, and this could be very damaging to our cellular material. So they just say in general here, these free radicals having unpaired electrons. Remember, unpaired electrons doesn't necessarily mean charged, it just means unpaired. They're very highly reactive, they're fast moving enough, and they're very chemically active enough that they can actually damage our cells on the DNA level, a lot of our living tissues here, proteins, lipids, and as well one other one they show you with superoxide. They're just giving you some examples of potential because radiation has sort of activated these, interacted with the matter in your body. It can be very damaging to, I mentioned earlier, DNA, cells, lipids, things like that. So something just to keep in mind as we do this nuclear chemistry here. We want to make sure we design our power plants and work with it safe enough as we try to use it as a good energy source. So let's flip over again to the textbook slides. Okay, so continuing on with our fission lesson here. Remember from yesterday's lesson here, we had introduced here, we have what's called a band of stability. We have our stable elements on the periodic table here. They all exist in this sort of center band here. If they lie too far out on either side, if, for example, they have too many protons, so protons are plotted on the x-axis here. If I have too many protons, I actually want to alpha decay so I can get back to this band. If I have too many neutrons, I'm actually going to go beta emission here. So that's sort of one feature that talks about whether alpha and beta. In those cases, though, those are sort of radioactive processes that happen just on a really local scale. What we're doing today is we're actually taking actually the compound itself. We had uranium. Unfortunately, we saw some 99% of uranium was the unreactive form. We call the reactive form here the fissile form. So the fissionable material here, 235, we're going to see enriching as we flip to the next slide here, but enriching is basically selecting for going from the 238 form over to the 235, how can I get more and more of the useful form? And what I want to show you with this diagram here is, again, the 235 form, even though it is lighter, even though its binding energy is a little bit higher, in terms of fission, in terms of breaking up into smaller daughter nuclei, you end up seeing we actually get higher up on this chart here. Remember, higher up means more stable. What ends up meaning here is that's going to end up releasing off energy. And this is going to provide us the nuclear energy. So Let's have a look at those two main designs for a power plant. One was using this uranium field like I just mentioned, and the other with those plutonium breeder reaction styles. You're going to skip ahead in your notes here. We're going to come back in tomorrow's lesson to look at this part here is actually on fusion. So we'll come back to this tomorrow. So you can skip over it for now here. We're going to look mainly here at fission, so breaking apart. So again, this is just some more broad strokes here, how our common power plants design using this design as well as the reactor design. So what they're telling you here is nuclear fission can occur naturally. So sometimes you have just so happen to have free moving neutron, it ends up hitting a uranium. But what we're going to do is we're going to purposely control how many neutrons are put in. What's important for you to note here is for those neutrons, we want those neutrons, usually for this design, we call these neutrons, we want them to be slow moving neutrons. If they're traveling too quickly, they're just going to bounce directly off the uranium-235. It's not going to get a chance of actually being absorbed. So we're going to actually have control rods and moderators to actually slow that down. Let's look through some of this detail here. So I send in one neutron. So we had that picture, take the 235, take the fissional form. I have a slow moving neutron. You notice in this case here, we break up these guys here. We're going to call them daughter isotopes. Again, it's not always going to exactly be these particular chemicals. The daughter isotopes don't have to be similar in mass, but just if you're looking at a sort of conservation argument here, although I was uranium on this side and I'm not uranium on this side here, I can take, let's say, 92 protons. If I add up 56, 36, well, this neutron here doesn't have any mass here. That should amount to the same number of protons. The protons had to go somewhere. You could do neutrons as well. You could go 235 minus 92, how many neutrons, how many neutrons. I find it probably easier just to look at mass number. So I have a total mass 235 plus 1. I have a total mass of 236. What you're going to find in doing this here is when you add up this part here, that's going to add up just to 233. Well, where did the additional mass go? You might be tempted to then say, oh, I need to have a neutron that have 3 units of mass. Well, a neutron doesn't have 3 units of mass. Neutrons always only have 1. But what's going to happen here is I can release off 3 individual neutrons. So what's happening here is I had one of these ones here, I fired a slow moving neutron, and this one here ending up shooting off 3 other neutrons, and those neutrons are now ready to collide with something else. So just be careful when you're doing this conservation of subatomic particles argument here. Careful if you have a coefficient out here, this scales into it completely. That would mean I have 3 mass units because each neutron leaves with 1 mass. So when we actually look at our power plants here, we design it so that on average, we hope only 1 neutron initiates a further reaction. So in this schematic here, 1 neutron has generated 3. We want to have control rods enough to end up soaking up some of these extra neutrons. We don't want those to actually run into other particles here, so that only 1 on average goes to trigger another one, and in that case there we would have a critical mass of it. So we can use graphite, so just pure carbon or cadmium here, control rods. They absorb the extra neutrons so that we don't lead to, if it's out of control here, not only is it the chain reaction that we want, it might lead to what's called nuclear meltdown, and we definitely don't want that to happen. So we had those control rods here. Again, there's a conversation around, well, what do we do with all the spent control rods, all this waste here? We needed it to harness our nuclear energy, but once it's sort of depleted and used up, what do we do with the leftover waste, which many times is also very radioactive? We mentioned the term here, critical mass. Critical mass here is the minimum fissionable material that you would need. So you want to make sure that there's a good enough chance that a fissile material can find another nuclide before leaving the whole sample itself. So far they've introduced to us 2 words here. One is control rods. Control rods are used to control how many neutrons. They're going to use this term here, moderators. Moderators are used to slow down so that they can initiate further reactions. So we want to sort of have as much control as we can to sort of direct 1 neutron to interact with just one of them. I want to make sure I slow this one down enough so that the neutron has a good chance of actually capturing that neutron there. So there's some engineering aspects here. We want to talk about how we input the fuel, what shape do we make the container in, what's the path that the neutrons have, and the neutron speed or so. Those are all sort of designs to think about. For us in chemistry here, what we're interested in more so is we're interested in key terms like, oh, we need to actually enrich uranium fuel. Unfortunately, the uranium-238, this is 99% of our universe. Unfortunately, that's not the fissionable form. Enriching is trying to take this form here and selecting for the more useful 235 form. Here's the problem again, because they are isolated from each other, they're going to have similar valence structure, they're going to have similar outer shells, they're going to bond in very similar ways. So what we're going to do instead is we're going to leverage some physical characteristics. We saw two different ways here. First physical characteristics was forcing them through a semi-permeable membrane, and the other one here, I don't know if I have it, down here. It's going to be centrifugation. So these are leveraging physical techniques to try to separate these two. However, we saw just a little bit of math. I'll show it to you again here, but we need to repeat this many, many times so that I can successively select for more and more and more each time. We talked about here not just using just plain old uranium. That would probably just be chunks of solid. It's much easier to run through my design with gas because they already have the kinetic energy. Not only is it easier to sort of shunt through the rest of your power plant, it also is easier to utilize. So just like the slides here, they contrast two possible compounds. The compound that we're going to work with is going to be UF6. The nice thing about UF6 here is, again, it is covalent. Even though we would expect it has a lot of charges, the London forces here should be really strong. Because the fluorines here are super negative, these fluorines are going to really repel the other negatives here, and that's going to amount to very, very weak London forces between the two. Which is why this one here sublimes at some, like we said before, slightly hotter than room temperature, doesn't take much. Let's contrast that with UO2. UO2 is actually an ionic compound, we had said, because the UO2 ends up forming a lattice, so U+4, and there's a bunch of oxygen atoms interspersed. I don't know exactly how the bonding, but because UO2, just as a comparison molecule, is an ionic compound here, that's going to be much harder to work with. Now, we still have a problem. Even if we want to use this compound here, UF6, it's nice, it has low London forces, I still potentially could have the 235, that's the one I want, or I could potentially have uranium-238 in this UF6. So I haven't dealt with my problem just yet, but at least I now have a compound that's at least gaseous, so it's a little bit easier to work with. Let's have another look at how they calculated that 1.004 in that schematic that we had earlier. This guy here is actually called Graham's law. We're going to start off, it's actually a fairly simple derivation here. We're going to imagine sending through our chemical here all at the same temperature. And what's going to happen here is our chemicals are always going to have the same average kinetic energy because temperature is a measure of average kinetic energy. So what I can do here is I can say, what's the kinetic energy of the 235 form? That has to equal the kinetic energy of the 238 form. We know from our physics, our kinetic energy is half mv squared equals, color coded here, half mv squared. The only difference here is the mass. So this is the 235 form. This one here is the 238 form, just to get rid of the halves here. And then I'm going to bring over here, so here v squared. This one here is of the 235 form. I'm going to bring over the velocity of the 238 1 squared. I'm going to bring the mass term to the other side. So the mass of the 238 divided by the mass of the 235. And then like we saw on the PowerPoint here, if I want to find the velocity of the 235 form over the velocity of the 238 form, it's actually going to be the square root. It's the sort of inverse relationship of the mass of the 238 divided by the mass of the 235. So again, we see the opposite relationship. We're going to see that this speed here is actually a little bit faster because it's a lighter atom, even though based on the kinetic energy, their kinetic energies are actually equal on both sides. So we can do that again in more detail here. Again, the mass is not just going to simply be 238 and 235. What we're going to actually need is we need to punch in, I have uranium F6 like this. So the uranium would be, this part here would be that 238 in this case here. Fluorine still have a mass 19 times 6, so that was some 300, I think 350, something like that. And that's where we ended up with that 1.004. What I want to just show you here is you can also, so that's nice, this Graham's law, it sort of does this inverse relationship between velocity and mass. What we can sort of liken it to and make it proportional to here is if something ends up traveling faster, it's actually going to take less velocity, and the time is actually going to be inverses of each other. So what's happening here is because, let me just write this down in words, maybe it's easier. So because this one here is lighter travels faster, so takes less time. So because it's traveling faster here, every time I punch it through a semi-permanent membrane, it separates a little bit. There is this 1.004 time ratio if you do this math here, and you end up seeing, well, if I can cycle it through many, many times, if I do it 4,000 times, even this really, really minor difference here will amount to enough that it can separate. I can actually increase the amount of uranium-235 to a more useful form here. 4,000 times, you might imagine it gets a lot, but because this time ratio is so tiny here, we actually only get it up to about 3 to 5%. Worrying about sort of nuclear weaponry here, to actually weaponize uranium, they say you need it enriched upwards of like 20%, 30%, which is why it's not as a big consideration, because it takes a long time to get the radioactive form for weaponizing. Centrifugation, as we mentioned here, utilizes the same sort of physical characteristics, but this time it's utilizing their masses and the densities to actually separate. So in this case here, if I have a heavier uranium isotope here, as I punch it through, we had that nice little schematic on our PowerPoint here. The 238 form actually ends up going through a much larger, 238, much larger cycle than, say, the 235 form. 235 is a little bit lighter. It ends up traveling through a smaller radius. And if I can engineer it in such a way here, because the lighter one here can be pumped out with a smaller radius, again, I'm still going to have to repeat it many, many times. What they're going to do is they're going to cascade the centrifuges. After traveling through this one, they travel through another one, travel through another one. They're going to cascade through 1,000 centrifuges, and again, what's going to happen is steadily but surely it does slowly enrich, and we get the more useful form. Then we can do this sort of, once I have the more fissile form, I can do the neutron capture. Let's contrast. So that was sort of the first design here, using uranium source directly. We sort of introduced it as one of the potential wastes out of this one here, unfortunately, is actually plutonium. So they actually demonstrate this reaction here. Uranium-238, if I just run this through a neutron, this is actually going to how I'm going to create more fuel, but we'll notice that over the course of this reaction here, what we can do is we can actually do this chemical reaction. I can, instead of doing the neutron capture on 235, if I send a neutron to the unreactive, so make a note to yourself here, this is the unfissile form, this is the one that wasn't radioactive. If I let this do neutron capture, over the course of the reaction, I end up getting a slightly heavier isotope. It ends up beta decaying here into neptunium, and we see neptunium ends up generating some plutonium ingredient. And this one here is actually going to be the reactant for our breeder reactions. In this case here, it's much quicker than the uranium design, because this fuel here can be produced by neutron capture, just like we saw here. The breeder reactors convert the more abundant 238 into fissionable. So sure, the 238 form here wasn't really radioactive, but we convert it into plutonium, which definitely is. In this case here, we actually do want faster moving neutrons. So even in terms of equipment-wise here, we don't actually need those moderators to actually control the speeds anymore. Although there are, again, this is sort of nice, so you can make a note to yourself here. No need to enrich, so I don't need to wait for this cascading, whether it be Graham's law or whether it be centrifugation, because the plutonium directly itself can react, and because plutonium is a totally different chemical from uranium. Let me just actually write this down for you here. Because plutonium and uranium are different chemicals, they can be separated by chemical reactions. So we're not just leveraging those physical characteristics here. There are reactions that uranium does that plutonium doesn't, and vice versa. Even if I start off with uranium-238 and somewhere along the way it ends up producing plutonium, if I can use a chemical reaction, break bonds and form bonds, and I can select for 239, I don't need to wait just for these physical ways to actually separate. So that's another advantage for plutonium. Now, some disadvantages, however, here is plutonium. As we know, it's very toxic just to work with, so a lot of safety precautions you need to be careful of already. In this case here, because it doesn't need that enriching here, there is worry that it's much easier to weaponize. It's much more susceptible to accidents, so some sort of accidents that we can have here. We have to use coolants for this design here. We typically use alkali metal coolants. We learned in Chapter 3 alkali metals tend to react really violently with water. So if, unfortunately, I have liquid escaping sodium and it encounters any water, whether it's in the atmosphere or whatever, that could be a dangerous situation that we have. So just to show you that even though plutonium is sort of a nicer design, it doesn't rely on this enriching process here. It's this sort of fissionable material. They say here in World War II they actually utilized both designs, but this one here is more susceptible to accidents. So always a consideration here of safety aspects here. We're going to talk about sort of waste storage in the next lesson as well. I'm going to jump down just to a little bit here on the next page here. If you just contrast the fuel sources that we talked about so far in this unit, so far we've been talking about fossil fuels, which are chemical stores of energy. We had the problem of it releasing carbon dioxides and SO2s. Nuclear fission here, it doesn't end up releasing those possible global warming gases. So unfortunately, though, those products here tend to be radioactive. Even though it's a waste product, we said plutonium was a waste product, we managed to sort of recycle that there. But what about all the bariums and the other daughter isotopes that we formed? Those typically are also radioactive and typically have very long half-lives as well. For fossil fuels, any sort of incomplete combustion, it ends up leaving a lot of particulates in the air. That might be good in terms of a global warming aspect. It sort of scatters some of the solar radiation. We'll see that in a later lesson. Burnt in air, so it needs oxygen. We can recycle some of the materials, whereas nuclear fission, again, we're utilizing, here's a key term, fossil fuel was burning chemicals, whereas nuclear fission is using the mass defect, using this change in binding energy and leveraging that there. It's good, right? It provides tons and tons of energy. We're going to see, especially with fusion for tomorrow's lesson, it actually provides all the energy that we would ever need if we can harness it properly, but it also comes with some downsides as well. We need to talk about how do we do waste storage, how do we dispose of it, possibilities of meltdown, safety considerations, especially with those breeder designs. And on the PowerPoint, you can read through just a little more section here on the bottom, especially because this ionizing radiation is so energetic. It can actually interact with the water molecules in our body here. It can end up forming just a plain old ionization energy kind of reaction. It can end up forming hydroxy radicals, even oxide radicals. There's a couple other ones here, and just in general, they're energetic enough to actually damage your membranes, damage your nuclei and whatever. These are sort of some of the outcomes just to be careful of when we're working with radioactive designs. So we do want the energy, right? That's why we're studying this, but there are a lot of safety considerations and precautions to be careful of, right? So I'll leave the lesson off there. If you have any questions, just let me know. Thanks, guys.